All right, so the first part of Unit 3 is going to focus on just some general terminology and some review calculations with thermodynamics, which is the study of heat and work. We have to consider both the system and its surroundings to be able to understand what's going on in a problem involving thermodynamics. Sometimes we're going to be looking at characteristics of the surroundings to help us find out things about the system, or we could be looking at it in the other direction. So the universe makes up both of those. The system typically is, your reaction, whatever change is occurring. This could be a physical change as well, but basically whatever's being studied. And the surroundings are anything outside of the system that is able to interact with it and exchange energy. So here we have a chemical reaction that's taking place in the solution. The surroundings would be the aqueous environment in which the reaction is taking place, so the water, as well as like the air, um, anything that is not directly involved in that chemical reaction. The system would be the chemical reaction itself. So that would be your reactants. When we are talking about system and surroundings, we are going to focus on what is undergoing the chemical change as being our system, and then the surroundings as what surrounds it. And a physical change, it will most likely those involve like a metal and a water or something like that. The metal typically is going to act as our system, and then the water would be the surroundings because the water is going to take in heat or release heat to the metals or in the solids in those scenarios. So just like conservation of mass, conservation of energy states that you can convert energy from one form to another, but when you do that, the total amount is conserved. Energy can be transferred as heat, especially when you are in a warmer environment and there is a colder environment surrounding that object. Some practical examples I always refer to, hot cocoa in the winter, heat's going to be released from the hot cocoa to the cold air surrounding it. Or in the summertime, if you have an iced drink, that iced drink is going to build a condensation on it. It's going to get warmer because the hot air that's surrounding it is going to transfer heat to that object. So heat's always going to move from warmer to cooler, and it's going to continue to do that until the objects are at the same temperature. They are in thermal equilibrium. The object that was initially at the higher temperature to start with will lose thermal energy, while the object that was at the cooler temperature to start with will gain it. When you lose energy, you're undergoing an exothermic change. When you gain it, you're undergoing an endothermic change. So when we think about this in terms of the system and the surroundings, if the system is giving up energy in an exothermic change, the surroundings will take that energy in because the two together make up the universe, and you cannot lose energy out of the blue and you cannot create it. In an endothermic process, you are taking in energy, the system's energy is increasing, so that means that the surroundings would have to decrease in energy. One way we are able to ascertain energy changes is through specific heat capacity. That's when we're undergoing a temperature change. When we talk about phase changes, we're going to do something a little bit different. Also remember that heat and temperature do not mean the same thing. Heat is a calculated quantity. We can calculate it by ascertaining changes in temperature or examining what's happening when a substance changes state. And when we get into chemical changes, we will see how you can examine that looking at the energy changes associated with bonds being broken and bonds being formed. Okay, so when we're dealing with physical changes, which is where we're at right now, three things are going to influence how much heat gets transferred when an object is being heated or being cooled. How much of the object you have, its quantity, its mass, the temperature change it undergoes, and also its identity. And the identity is going to play a key role with your specific heat capacity. Your specific heat capacity is the energy that gets transferred as 1 gram of a substance is changed temperatures by 1 degree Celsius. And because Celsius and Kelvin change by the exact same value, that could also be 1 Kelvin. So for specific heat capacity, if you see units in joules per grams Kelvin or joules per grams degrees Celsius, um, you do not have to do any crazy conversions because we're dealing with a change of temperature by 1. We don't have to do any conversions with our temperatures. And this specific heat capacity works whether you are raising the temperature or whether you are cooling it down. There is a table in your textbook just as a reference, but the problems I'm going to give you, you're not going to need to use it. Just letting you know that that's there. When you're dealing with molar heat capacity, it's the same type of quantity as specific heat, but it's just per moles. That's the quantity that is used. The size of your specific heat capacity has a lot to do with the type of substance you're working with, and we'll spend some time a little bit later talking about this. It's intermolecular forces. If it is a substance that is more likely to stay intact, that's going to be held together more strongly, it's going to have a higher specific heat capacity. And if it's a substance that's able to change temperatures a little more readily, it has weaker intermolecular forces holding it together, it's going to have a much smaller heat capacity. Again, just a reminder that if the system's losing energy, the surroundings has to gain that quantity in equivalent, or if the system is losing energy, if the system's gaining energy, the surroundings have to lose that energy. So if you like the triangles that you might have seen in your first chemistry class, this is one for that particular equation. Q equals mCp delta T. Hide the variable you're looking for, and it shows you how to arrange the variables for the one that you're solving. So an example we're going to work with, just making sure you're comfortable with that equation. 1250 joules of energy is needed to heat a sample of pure gold, 0.129 joules per gram Kelvin, from 12 degrees Celsius to 15.2 degrees Celsius. We want to calculate the gold's mass. So our temperature change, we have the two temperatures. I'm sorry, let me start back. Our equation is Q equals m Cp delta T, and we want to solve for m. So in this problem, we need to find quantities for Q, for Cp, and for delta T. We know the energy amount that was needed to heat the substance. We're told it was 1250 joules. We have the heat capacity for gold, the 0.129, and we have the two temperatures that the gold changed between, 12 degrees Celsius to 15.2 degrees Celsius. So if we want to solve for M, we want to bring Cp and delta T underneath Q. M would be equal to Q over Cp delta T. So my Q would go on top, the 1250 joules. My specific heat would go in the denominator, the 0.129, and my temperature change, which would be 3.2 when I subtract those two temperatures, would go as well in the denominator. Why did I write the units for Cp the way they did? I wanted you to see how they canceled out. The joules are gone. And remember, because this is per degree Celsius, it's a change in temperature. It does not matter that Celsius and Kelvin are in different temperatures or units. They would cancel each other out, because if you change those two Celsius temperatures to Kelvin, you would still get the same net difference. The only time you would have to change the temperatures is if you were like subtracting a Celsius from a Kelvin. Then you would have to have consistent units. When I go through and do my math, multiply and divide, I want to have 2 sig figs because of the 3.2. I have 3 sig figs in my Q and 3 sig figs in my heat capacity. And so I got an answer of around 3,000. And to round that to 2 sig figs, that would be written with 3,000 with a line over the first zero, or 3.0 times 10 to the third. This time I do want to calculate a temperature. It says calculate the initial temperature of 150 grams of silver. You have a Cp value of 0.24 joules per gram Kelvin. If 1.8 kilojoules of heat was used to warm the silver to a final temperature of 85 degrees Celsius. So we want to find temperature, and the only temperature component in our equation is delta T. So we're going to start by solving for delta T. You could go ahead and solve for initial temperature in this if you chose. I'm going to go ahead and just solve for delta T, and then I'll get my initial temperature from that. My Q again needs to be in joules. I have that 1.8 kilojoules. My specific heat is 0.24, but notice that that is in joules. If you have a different unit for your Q than you do for your CP, you do need to make sure those units are consistent. And then I have my mass, the 150 grams. So I'm going to take my Q, or so my delta T is what I'm solving for. So I'm going to take my Q and divide it by M and CP. 1800 joules. Notice I changed that from kilojoules to joules by multiplying it by 1,000. I'm going to divide it by my mass, 150.0 grams, as well as my CP, 0.24. The joules cancel, the grams cancel, and I get a net temperature change of 50 Kelvin. Since the net temperature change is 50 Kelvin, the net temperature change in Celsius would also be 50 degrees Celsius. And I know what my final temperature was. I know that it was 85. And delta T is just final minus initial. So since 50 Kelvin, that change is the same as 50 degrees Celsius, and that my final temperature is 85, I can use those two quantities to solve for my initial temperature, which would have been 35 degrees Celsius. And so this is showing a way that we can look at temperature changes, or a way that we can better measure how heat is being transferred via temperature between the system and the surroundings. Styrofoam cups are really good insulators. We've got the thermometer in there, and we've got a stirrer, so we've got the cork stopper on top, so we can minimize heat loss from the surface of the coffee cups. So this is a really good way to get a better understanding of where the temperature falls. You do have to keep in mind that you have to mix the materials together, so you are going to have a little bit of heat loss just from the initial pouring the chemical in and then putting the cork stopper in place. And so this will be our final example, and this is one where we can use that MCP delta T equation to compare the system to the surroundings. We have a nickel metal, 15 grams, that got heated up to 100 degrees Celsius, and it was added to 55 grams of water, which was at a temperature initially of 23.0 degrees Celsius. We're going to assume that all the heat was lost by the nickel, was absorbed by the water, and calculate what the final temperature was of the two. Remember, when heat is being lost to something, is going to get to a point where they're both at the same temperature. So final temperature for both the nickel and the water will be the same. We do have the two specific heats, 0.444 for nickel and 4.184 for water. So as a visual, there's your 15 grams of nickel with the initial temperature of 100 degrees. There's your 55 grams of water with your initial temperature of 23 degrees. And we're going to mix the two together, and we want to find out what that final temperature will be. I also want to remind you that the system and the surroundings should have the same amount of heat. One's losing it, one's gaining it. So when you put the two together, the net change should be zero because conservation of energy should apply. So if I'm going to solve for one of these in terms of the other, it doesn't matter which one you make negative, but one of them would have to be negative since heat lost is going to be a negative value, and the other one is gaining the heat, which would be a positive value. So you do have to set one, if you're going to set them in terms of each other with a physical change, one's got to have that either absolute value or have a negative sign. Well, we know that Q is equal to mCp delta T. The amount for Q for both should be the same, but how we go about solving it's going to be a little bit different because we have different masses, different heat capacities, and different initial temperatures. So we're going to have to plug in quantities for all of those pieces. And we have all those quantities. The only one we don't have is the one we're solving for. So we have that the mass of our initial metal was 15 grams. That specific heat capacity was 0.444. I went ahead and changed that to Celsius for this example since the temperatures are in Celsius, and we are going to have to do some addition. It doesn't matter whether you change it or not. And then we're going to plug in our initial temperature of 100 degrees Celsius. We know the mass of our water was 55 grams. The specific heat of our water was the 4.18. I used 4.18 in the problem because that's what I use in Gen Chem. I don't even think about it. You can use 4.18. You can use 4.184. It is not going to have a drastic change on your answer. And then I know the initial temperature was 23 degrees Celsius. Now I'm going to work you through the algebra for this just because I've got it in this slide presentation. But honest to goodness here, you can stop. And you can put these two equations in your calculator. You can put in your calculator, you can plug in the first equation for y1 and the second equation for y2, plugging in x for your t sub f. And then you can go, once you have those two equations plugged into your calculator, you can go to second and trace. And you're going to have different options there for calculating, and you want to find the intersection. So you're going to hit 5, and you're going to give your calculator a second to pop up, and it's going to ask you, what do you think of this value? And you're going to hit enter 3 times. So I've done this way more than I want to think about. And when you get through and you've hit enter 3 times, it will give you a value for your temperature change. And it might be a little bit different than mine, and that is okay. I will caution you that if your value does not fit in your Windows screen, it may say that there's some sort of error. You get to your window, obviously, by clicking the window button at the top of your calculator. And what I typically do if that is the case is I just change my X-min and X-max, my Y-min and my Y-max to negative 100 and positive 100. I just give it plenty of room to make sure that it can graph everything. So that is an option for you. If you want me to show you that in class, I'll be more than willing to do so. But if you went through and did the algebra, we know how much we like algebra. So a lot of chemistry is good applied algebra for you. So I just combined the constants there, and now I'm going to distribute through. This is why I went ahead and changed the temperatures to Celsius. Now I'm going to combine my like terms now that I've gotten everything distributed through on both sides. And now I can solve for TF, and I get that it's a temperature of 25.1 degrees Celsius.